are some examples of solving polynomial equations. First, let's take a look at this fundamental theorem of algebra. It says that a polynomial equation of degree n will have exactly n solutions. That might be something that you've figured out already, but let's take a look at a couple of examples to see if we really believe this. Take a look at this quadratic equation. X squared equals negative 16. Your first instinct might be that you're going to say that this has no solution. Well, really, there's no real solution, but there are two solutions. They're just both non-real. If we square root both sides, we can see that x is equal to the positive or negative square root of negative 16, which is plus or minus 4i. So it does, in fact, have two solutions. It's just that they're both non-real. And notice this was a quadratic equation, and it did have two solutions. How about this equation? X squared minus 6x plus 9 equals 0. We could solve this quadratic by factoring. This would become two numbers that multiply to 9, and add to negative 6 would be negative 3 and negative 3. So this is really the quantity x minus 3 squared equals 0. So you might say that this has only one solution, just x equals 3. And yeah, that's correct, but notice that x minus 3 factor showed up twice. So this is really like a double root of the equation, or you could think that it has a multiplicity of 2 if you're thinking about the zeros of the function if you were to graph it. So even though you might think that there's only one solution, really there are two because it's a double root. So it is true that a polynomial equation of degree n will have exactly n solutions. We just have to remember to include non-real solutions as well as those multiple roots, just like the two examples that we just saw. So let's solve some interesting polynomial equations. Let's look at this one. X cubed equals 8. By our fundamental theorem of algebra, we know it has to have 3 solutions. So we can't stop solving until we've got our 3 solutions. Can you think of one solution? Well, there's an easy one out there that you probably already know. X equals 2 works here because 2 cubed is in fact 8. But what are the other 2? We can't stop until we have 3. One way of thinking about this is maybe getting the right-hand side equal to 0. X cubed minus 8 equals 0. Now, solving this polynomial equation has boiled down to finding the zeros of that polynomial function. X cubed minus 8 equals 0. We're looking for the zeros. Remember, before, we know that if x equals 2 is a 0, then the expression x minus 2 must be a factor of x cubed minus 8. And we're going to use that fact to find the other 2 solutions to our equation. So what we did was we found one solution. Then we realized that that must mean x minus 2 is a factor of that cubic. Well, if we know something is a factor, how could we find maybe the other factor? X minus 2 times what gives us x cubed minus 8? We can use division. And I'm going to use synthetic division because we can here. X minus 2 is a monic linear expression. So I can put the 2 up in the corner. And we're now going to do, let me write out what we're doing, x cubed minus 8 divided by the quantity x minus 2. That's what we're going to figure out now. Put the 2 up in the corner. We want to put our coefficients of x cubed minus 8 lined up. So there's a 1, 0x squared, 0x, and negative 8. That right there is sometimes the trickiest part, remembering that there's no quadratic term in x cubed minus 8 as well as no linear term. So we have to put the zeros in there as placeholders. Bring down the 1, multiply, add, multiply, add, multiply, add. I'm really glad we got 0. In fact, if we didn't get 0 as a remainder, something would have been wrong, because I did this division under the assumption that x minus 2 was a factor, so I knew that we had to get 0 as a remainder. So our quotient here is x squared plus 2x plus 4. What that means is x cubed minus 8 is equal to the product of those two things, x minus 2 times x squared plus 2x plus 4. And if you distribute this all out and multiply, you'll realize that this is, in fact, an identity. That is true. So now, since x cubed minus 8 equals 0, we know that, let's see, so our equation now looks like this. X minus 2, x squared plus 2x plus 4 equals 0. By our zero product property, either our first factor is 0, in which case x equals 2, or our second factor equals 0. So now, it's really just come down to a quadratic equation that we have to solve to get our other two missing solutions to that original polynomial equation. Can we solve this by factoring? Are there two numbers that multiply to 4 and add to 2? No, this is not factorable. So we could use one of our other methods. I'm going to use the quadratic formula here. X equals the opposite of b, plus or minus the square root of the quantity b squared minus 4ac. 4ac is 16. Doing a little bit of the arithmetic in my head. All over 2a. That's negative 2 plus or minus the square root of negative 12 all over 2. And we can keep simplifying this. Notice we have a square root of a negative here. That means that this must be a non-real solution. We have a non-real part here. So let's simplify that. Negative 2 plus or minus, let's see. I know 12 we can reduce to 2 root 3. Sorry, root 12 is 2 root 3. And then since it was root negative 12, that's going to be 2i root 3 all over 2. And then I can divide each term in the numerator by 2. And these are our other two missing solutions. It's kind of strange. You wouldn't think that negative 1 plus I root 3 cubed equals 8. But it does. You can try it. Same thing with negative 1 minus I root 3 cubed. That still equals 8. So our three solutions were x equals 2. Kind of by inspection we realized that. X equals negative 1 plus I root 3. And x equals negative 1 minus I root 3. Those are our three solutions to x cubed equals 8. We found one, used division to find our other quadratic, and then had to solve that quadratic. Let's do another kind of funky cubic polynomial equation. How about this one? 5x cubed minus 2x squared plus 15x minus 6 equals 0. Can you just guess a solution like we could before? It's a little bit trickier. Turns out we can actually factor this by using factor by grouping. We can group the first two terms. I draw that line to kind of separate our equation. If you look at 5x cubed minus 2x squared, what do they have in common? They have an x squared in common. What's left over when we factor out that x squared is a 5x minus 2. Take a look at the second group of two terms, 15x minus 6. They have a positive 3 in common. What's left when we factor out the positive 3? A 5x minus 2. That was really handy, because now I see a 5x minus 2 in the first term and a 5x minus 2 in the second term. We can actually factor out that binomial 5x minus 2. And we're left with the x squared plus 3. Notice we factored that cubic. If that didn't quite make sense to you, here's another way of, sometimes it's kind of hard to see that factorization. Let's let the whole 5x minus 2, let's let that equal triangle. So that way, we can think of this as x squared times triangle plus 3 times triangle. Now do you see how we can factor out a triangle from each of these two terms? I'm just letting it stand for some funky symbol. So here, since the triangle was 5x minus 2, you can plug it back in instead of the triangle and get this factorization. But now, again, we can use the zero product property to solve this. Either 5x minus 2 equals 0, or x squared plus 3 equals 0. If 5x minus 2 equals 0, then x is 2/5. There's one of our solutions. If x squared plus 3 equals 0, then x squared equals negative 3. X equals plus or minus I root 3. How many solutions do we get? We got 1, 2, 3 solutions, which makes sense because we had a cubic equation. We needed to have 3 solutions. Let's do an example of a quartic polynomial equation. How about 9x to the 4th minus 3x squared minus 12 equals 0. Let's see, factor by grouping wouldn't make sense here because there's only 3 terms. We can't group 2 and 2. I can't really guess a solution right away like we did with the first example. It's kind of complicated. This is a quartic, but it's a very special quartic. It's kind of like a quadratic-y quartic. I mean, we're missing the cubic term, we're missing the linear term. It almost looks quadratic. So a trick is to actually make it a quadratic. 9x to the 4th, if you recognize that that's the quantity 3x squared squared, that makes things a lot easier. And notice that 3x squared shows up again in the second term. So by rewriting that quartic as really a quadratic in something squared, then now we can actually factor this. So in other words, let's let 3x squared equal our triangle. Now can you see that this is really triangle squared minus triangle minus 12 equals 0. Same this idea of chunking. And notice that 3x squared squared, the quantity 3x squared squared, does equal 9x to the 4th. So we haven't really changed anything yet. But now I can factor this using triangle. Two numbers that multiply to negative 12, add to negative 1, negative 4 and 3, triangle minus 4, triangle plus 3 equals 0. So triangle equals 4, or triangle equals negative 3. But we weren't solving for triangle, we're trying to solve for x. So let's now plug 3x squared back in for triangle. Either 3x squared equals 4, or 3x squared equals negative 3. That means x squared equals 4/3, or x squared equals negative 1. So x equals plus or minus root 4/3, or x equals plus or minus root negative 1. We can simplify this a little bit. I'm not going to bother rationalizing the denominator here, but we can take the square root of 4 over the square root of 3, which gives us the square root of 2 over root 3. And in this case, root negative 1, that's just I. Here are our solutions. How many solutions did we get? We got 4. 1, 2, 3, 4. That makes sense because we had a quartic equation to begin with. So those are 3 kind of very specific examples of polynomial equations that we are able to solve by hand. Of course, we can solve any polynomial equation using the intersection feature on the graphing calculator, but here are some nice factorable examples that we really can do by hand. So good luck with those.